Diviner is an infrared radiometer designed to map the surface temperature of the moon. To date, there's never been an instrument like Diviner that has been able to have the capability to map the entire range of surface temperatures of the moon globally.
Diviner measures thermal radiation from the surface of the moon, and it measures it at wavelengths beyond human vision, more in wavelengths that we would sense as heat. We tend to sense heat from very warm things like a stove or fire, but it turns out that everything in the universe emits thermal radiation no matter what temperature it is, as long as it's above 0. And so the moon, even in its coldest regions, emits thermal radiation that Diviner can sense and turn into a temperature that's relayed back to Earth.
So Diviner looks sort of like a pair of binoculars. It has 2 telescopes, and radiation comes into both telescopes and then is focused on a pair of detector planes that contain a bunch of filters that filter the radiation, and then we get a series of measurements in 9 spectral channels. 2 of these are devoted to reflected solar radiation, and these are sensitive to sort of the total amount of light that your eyes might see in the visible part of the spectrum. The remaining channels are in the infrared part of the spectrum, which are at wavelengths beyond those that the human eye can see. And these pick up radiation that's emitted from the moon, which increase as a function of how hot the surface of the moon is.
The primary operating mode for Diviner at the moon will be what we call nadir pointing push-broom mapping. This involves using the actuators to point the telescopes directly down at the lunar surface, right below the spacecraft. Each channel has a linear array of 21 elements, and we align those arrays perpendicular to the direction of spacecraft motion. So as the spacecraft moves, our arrays sweep across the surface, and we produce a map of a strip of the lunar surface. Over the course of the mission, we get many of these strips and put them together to form a full map of the lunar surface.
The Lunar Reconnaissance Orbiter primary mission is 1 year long, and that's designed to allow the instruments to get full coverage of the moon's surface at all local times on the moon. So anywhere on the surface, you want to see a whole day's worth of data. Now the moon's day is 1 month of Earth time. So the moon rotates on its axis with respect to the sun every month. So every month, Diviner is able to see the entire moon at one time of day, and then over the course of an Earth year, we see every point on the moon at all times of a lunar day. So it's kind of complicated, but the point here is that over a year, we'll see all points of the moon at all times of day, and that is what we really need to interpret the temperatures and the thermal history of the moon.
We periodically interrupt the nadir-pointed push-broom mapping to do calibrations. Every 10 minutes or so, we do what we call a radiometric calibration.
We have 10 radiometric calibrations per orbit, where we take Diviner and we first look at space to get a cold measurement. Then we look up into the instrument itself at our yoke, where we have 2 warm targets that we call black body targets that are usually about 300 degrees C. And then we look out at space again, and this gives us a 2-point radiometric calibration. Additionally, 1 time per orbit, we do a photometric calibration where we will rotate Diviner in azimuth into a position where our solar calibration target is illuminated, and then we'll view our solar calibration target and get essentially a white reference for our solar channel measurements. Diviner is on autopilot most of the time, where it does the same observation sequences over and over and over, and really we just tweak the timing of some of the different calibrations that we do. Now, occasionally we do things that are more intensive, such as taking a picture of the spacecraft by rastering Diviner across the spacecraft in both azimuth and in elevation. Or we could also look at the surface of the moon with from different angles within a single orbit.
Another thing we can do is to scan across the disk of the Earth. This is kind of an interesting way to look at the Earth because it's not unlike the way that someone on another planet might be able to view the Earth from a great distance with a large telescope. And this may be relevant to those that are looking for habitable planets elsewhere in the universe. because diviner's view is similar to maybe what you might be able to see from a distant planet.